Okay, our next speaker is Cipriano Cioffo from Università degli Studi di Padova, and they will talk about biased elementary doctrines and the quotient conditions.
Thank you, Nico. And first of all, I want to thank the scientific committee for this opportunity to speak today, and all of you who chose to spend this first last afternoon of the conference in this room. So, as that my talk is divided into parts. In the first part, I need to recall some well-known definitions and constructions in order to give you the idea of what was my problem during this work. And in the second part, I will give a solution to my problems. So, let's start from the definition of elementary doctrines. Okay, elementary doctrines were introduced by Lovire, and they turned out to be a very fruitful and easy tools to deal with logic in category theory. What we need, the underlying structure, is just a contravariant functor from a category C, which has finite products, into the category of infimum semilattices. You can think about the category C as the level of the context of your logical theory, and the values of this functor as the predicates in the context. Okay? So what does it mean elementary? It means that our structure is expressive enough to deal with the equality predicate. Okay? And this is required and this is obtained just requiring the existence for every object of our category of an element that we will call the favored equality in the fiber of x times x, which has a suitable property. So the one that you see on the screen here is the definition of Lovire, which requires an adjunction, but for the purpose of this talk, I will recall an equivalent formulation of elementarity, which was first observed by Maietti and Rosolini in this article, and you can find a proof of the equivalence in this other article of Pino, Jacopo Menegger, and Fabio Pasquale. So, what have we to require on this element, the favored equality? Just these three conditions. So, on the left you see the condition written in the language of the doctrine D, and on the right you have an informal internal language. Okay. So, the first one just states the fact that the favored equality is reflexive. The second one states that the fiber over X is actually given by the descendatum of equality. What does it mean? That every predicate over X that holds on an object X1 holds also on every other object X2, which is equal to X1. The third condition is a little bit syntactical, and we could read it like the product of the equality, or the component wise equality, implies the equality of the product, on the product. So, what it means that if you have two objects of X which are equal, and two objects of Y which are equal, then the pair X1, Y1 is equal to the pair X2, Y2. Very reasonable, no? And these three conditions, with these three conditions, you can derive what you expect from the equality predicates, such as the symmetry, the transitivity, and also the converse of this inequality, which means that if you have two pairs which are equal, then also the complements are equal. Okay? So, let's make some examples of elementary doctrines. The first one is one of my favorite, which is the elementary doctrine of weak subobject or variation, as called by Grandis. So, what you need is a category which has finite products. Sorry, I say the strong again. I should have mentioned in the first slide that during this talk, I sometimes could refer to finite products as strong finite products, but just because at some point we will deal with weak finite products. So, if I say strong finite products, I just mean finite products, okay? So, this functor takes an object of a category which means finite products and weak pullbacks to the opposite reflection of the slice of the category C over this object. And the action of this functor on the arrows F just given by the weak pullback. Okay, we take a variation, we take weak pullback, and we obtain this variation. And very similar example is that of the subobject doctrines. Okay, and you here need a category which is left X out. It works similarly, but instead of considering all the poset reflection of all the slice, we just take the monomorphisms, okay? And the action is given by the pullback instead of with pullback. And for those examples, the elementary structure is given by the diagonal arrow. Now I give you two examples from type theory. So if you are not familiar with type theory, dependent type theory, just consider that in type theory we have these objects which are called types, but we can also have types that can depend on other types. That's why dependent type theory. And if we, for instance, consider the Martin-Löf type theory, I just take the intentional for my purpose, we can build the category of closed types and terms of function extensionality. And we can consider the functor which sends every closed type, which is a type in the empty context, to what? To the, let's say, the poset reflection of the types depending on X, what you expect. And the action of this functor on the arrows is just given by substitution. Okay? The last example, which is still from type theory, comes from the intentional level of the minimalist foundation. The minimalist foundation is a theory introduced by Maietti and Zambini, and later formalized by Maietti, which is a theory proposed to set first order constructive mathematics. Okay? And actually I need just to fix the notation. Okay, just remember that this G and TT from this category, which is very similar in principle to the first example, it gives rise to another elementary doctrine, and both of these examples have the elementary structure given by the identity type. But the fact that I have to, or at least I think that it's necessary to cite this example because it's the motivational example which lead to Pino and Milli to define what is the elementary quotient completion. Okay, so the minimalist foundation is the motivation for developing this theory. So what is the elementary quotient completion, which was defined in this article? Is a construction which turns an elementary doctrine into another elementary doctrine, which has this time well-behaved quotients of equivalence relation. What does it mean in this context, an equivalence relation? In the context of elementary doctrines, an equivalence relation is something within P equivalence relation, which means elements in the fiber of X times X, which has reflexive symmetry and transitivity condition restated in the language of the doctrine. Okay, now the notion of equivalence relation is relative to the doctrine. And you can define what is a quotient, which is an arrow which takes a related element into equal elements, which has a suitable universal property. And what you can do is to build another doctrine, P bar. And what you need are objects equipped with equivalence relation, arrows which preserve the relations, and on the fibers you put the descent datum of the relation, which are all the predicates of X, such that if the predicate holds on X1 and X1 is related with X2, then the predicates also holds on X2. Okay, and these constructions give you another doctrine which has well-behaved quotients of both of P bar equivalence relations. Okay, this just a remark. This is a construction which does not necessarily give you a category which is bar exact. Okay. Let's make some examples. The first one is the exact completion of a weak-relaxed category. So if we start from a category which has finite products and weak pullbacks, and we consider the variation elementary doctrine, we can do the elementary quotient completion. And what we obtain is the elementary doctrine of subobject of the exact completion of the weak-relaxed category C. And this is through the correspondence between the notion of pseudo-equivalence relation, which you use to provide the exact completion, with the notion of C or C equivalence relation. And this correspondence relies on the fact that we have finite products. Okay? But what happens? Not all the elementary quotient completion are exact completion. And this is the most important case. If we provide the elementary quotient completion of the elementary doctrine arising from the intentional level of the minimalist foundation, we obtain an elementary doctrine has well-behaved quotient, but this category is not exact. Okay? And this was used by Miglio to give an explanation of the interpretation of the extensional level of the minimalist condition into the intentional one. And also the elementary quotient completion of the other doctrine that I showed you actually gives you the setoid category. Okay? So let's go to my problem. When I was working on some doctrines arising from type theory, such that the last two that I show you, and what I wanted to do was to add well-behaved quotients to the slices of the base categories that I had. Okay? So the first thing that one can think is, okay, let's define what is the slice doctrine. Then later there is a slide explaining what is this functor, but this is the most obvious functor that you can imagine. And let's consider this functor, okay? Indeed. But the first check that I need to do is, am I working with a doctrine? Is this a category which has finite products? Well, if we have pullbacks, it is okay. But what happened in my cases, I just had weak finite pullbacks, okay? And this is because the intentional identity type gives you this, weak pullbacks, okay? But my problem reflects also in this general picture between the two constructions that we are dealing with. So on the right we have the elementary quotient completion by Miglio and Rosalini. On the left we have the exact completion of carbonic Italian of a weakly left exact category. So the second one is actually a generalization of, the one on the right is a generalization on the one on the left, at the level of the logic at least, because we are not forced to deal with the weak sub-object doctrine. But at the level of the context, let's say, it has more restriction. It means that we here have to consider finite products, but not necessarily on the left. Okay, so what I did was to try to extend the framework of elementary doctrines, considering functor from categories with weak finite products, and to provide an elementary quotient completion, an extension, which gets the full, which gets a full generalization of the construction of Enrico and Carboni. Okay? So this is now I start with the second part, and from now on we will consider weak finite products. And if you was in the room today at the Paolo's talk, you already recall what is a weak product, which means that a weak product of two objects, x and y, is another object with two arrows, such that for every two arrows of this kind, there exists, but is not unique, an arrow h, which makes this diagram complete. And in order to have a good insight of weak products, in order to understand, it's probably not a good insight, but I use this insight, this example that I'm going to show you, because it helped me with the terms that I'm going to introduce, which is this one. If we are in the category of sets, and we have two finite sets, a weak product of the two sets is just the product, for instance, of the two sets with another non-empty sets. For instance, let's take the two element set. And what happens in this weak product? The elements of this weak product are no more pairs of objects, sort of triplets. And what I see, what I consider, is that I have an object of A, an object of B, and a proof of the fact that these two objects make a pair. Okay? This is my insight for weak products. This is what I used. Okay? So for me, weak products as a sort of proof there. And what I defined is this structure, this definition of biased elementary doctrines, which is a contravariant functor from a category which is weak finite products. And I require what? For every object X and for every weak product W, the existence of an element, the biased fiber equality, which has to satisfy some property, in the style of the properties that I show you at the beginning of this talk. So, the first one is just the translation of the reflexivity of the equality using the fact that now we have weak products. So we don't have a unique diagonal. We have some arrows D which make this diagram commute. I just require this condition, which is the reflexivity. Okay? Condition 1 is equal to condition 1 of the first slide. Condition 2 is equal to condition 2 of the first slide. Again, I require that all the slide fiber of Lx is the descent datum of the quality. Well, condition 3 is actually I'm stating with condition 3 the fact that arrows preserve the equality, because W is a weak product of X with X. W prime is a weak product of X prime with X prime. And G, which is an arrow making this diagram commute, is based the rule of F times F. Am I requiring that the equality, if two elements are equal here, then their image is equal here, on W, okay? The fourth and the last condition is a little bit scaling. I don't want to go to the details, but consider that we have a weak product W of X and X. We have a weak product of W and W, so this U is also a weak product of these four elements. And I just need these diagrams because with the arrow T, I want to take the first and the third component, and the arrow T prime is used to take the second and the fourth component. Okay, so this is a condition stating that the biased fiber equality is the descent datum of something else that we can talk later if you want details. Okay, so with this definition, actually, we get that every elementary doctrine is a biased elementary doctrine. Okay, so the context has been a little bit expanded because actually we can reindex the equality of the elementary doctrine on every weak product. But another example which is very important is the fact that if we have a category which is weakly legs and we consider the variation factor, then we have a biased elementary doctrine when also products are weak. Okay? The equality this time is not given by the diagonal, but we need to take the equalizer of the projections. The weak equalizer, the equivalence class of the weak equalizer. This is the third example, which is actually what I was working on, which is the slice drop doctrine. If I start with the doctrine P, which has suitable condition, which gives me weak pullbacks on this category, what I can build is a slice doctrine, which is very obvious, an obvious factor. Takes an arrow X to A into the fiber of the domain, and reindex over the function F as the reindexing of F. Okay? And again, we can take the equality that is in the elementary doctrine P, and we can reindex it to obtain a biased fiber equality on the elements of the slice. Okay? But maybe it looks simple, but it is not, because weak products are very difficult objects to deal with. And this because we know that the fact that we drop the uniqueness of the arrow making this diagram commute implies several things. For instance, the fact that if we have two objects, X and Y, two different weak products are not necessarily isomorphic. Okay? And this means that the fibers over the weak products are not necessarily isomorphic. And the fact that if we have an arrow here which makes this diagram commute, if we have at least two arrows, for instance, the reindexing over these arrows are not necessarily equal to the reindexing of the object that are on this fiber along another arrow which makes this diagram commute. But the most important difference is the last one. The fact that here we still have that the equality on the product implies the component-wise equality, but not vice versa, which is due to this fact. Okay? We can have two triples for which the first two components are equal, but this does not mean that the two triples are equals. Okay? So the fiber-biased equality has this property, but not the other one. Okay? And for this reason, we call the equality on the product proof-irrelevant equality, and the product of the equalities or component-wise equalities, the proof-irrelevant one. Okay, what is a solution to do with this structure? A solution is to restrict our operation on the elements in the fibers of the white products to those elements which are called proof irrelevance, which I call proof irrelevance. These are been just taking the descent datum of the proof irrelevant equality, but it's now not important the details. The fact that is very important is that now, if I restrict to those elements which are proof irrelevant on the fibers of the weak product, what I obtain is that even if the fibers of two different weak products are different, then the restriction on these objects are isomorphic. Okay, so this is one hint of the fact that these are good elements to consider. But and we will denote this, let's say, equivalence class with this with PS of the list XY. But another more important property is this one, the fact that proof irrelevant elements are reindexed by projection. And what does it mean that two elements are indexed by projection? If we have a weak product of X and Y, and we have two arrows, such that F composed P1 is equal to G composed P1, and F composed P2 is equal to G composed P2, then the reindexing along F is equal to the reindexing along G. So this is the main reason which tells us that proof irrelevant elements are those that we need to work with in this bus structure. Okay? So, two examples. The first one is one who gave the name to these proof irrelevant elements, which comes from the slice of the doctrines arising from intentional type theory, which very briefly is what these are proof irrelevant elements of what? Of the weak product of these two arrows. The weak product of these two arrows as this domain, and the proof irrelevant elements are those times depending on X, Y, and a proof term of the identity, which is actually proof irrelevant. Which means that if X is equal to X prime and Y is equal to Y prime, are holes on this triple if and only if are holes on another triple which has X prime, Y prime, and whatever as proof term. But this, now we have another important example, which are the proof irrelevant elements of the doctrines of variation, which is very difficult to develop this, to adopt this definition. But what we proved in the end was that if we have a weak product W, the proof irrelevant elements of the weak product W are isomorphic to the cones on the two objects for which W is a weak product, and then we take the positive reflection. So this is a very clear condition, which is, we will see why it is so important. So, proof irrelevant elements allows us to make two main constructions. The first one is the strictification of a biased elementary doctrine. What is the point? I don't have finite products, I can freely add them. So, I can construct the category CS, whose objects are list of objects of C, and I can consider the functor PS, which takes every list into the isomorphism class of the proof irrelevant elements of the weak products of that list, which are well defined. And what we obtain is that if P is a biased elementary doctrine, then P con S is an elementary doctrine in the usual sense. And we have also this vice versa condition, which says that if R from the finite product completion is an elementary doctrine, then the precomposition with this functor is a biased elementary doctrine. Okay? And the second condition and the second construction that we obtain is the elementary quotient completion for this structure. But at this point, what is a P equivalence relation for a biased elementary doctrines? The definition of P equivalence relation relies on the fact that products were finite, okay, or strong. So, what is the point? Who are going to? So, for us, what are the P equivalence relation in this case? We need to reindex in a proper way this object, and so what we take are the proof irrelevant elements over the list XX. The construction is more or less the same of the elementary quotient completion, it's actually the same. And what we obtain that the P bar flat is what? Is again an elementary doctrine with well-behaved quotient. And we can also prove a universal property, which is actually those proved by Carboni and Vitali with left covering functions, which was talking about Giacomo before, but observe that this construction does not factors through the strictification, the elementary quotient completion. Okay? This process gives you something bigger. And with this advised elementary doctrine, advised quotient completion, we solved the problem that we had, which was taking the quotients of the slice doctrine, which actually is isomorphic to the slice of the quotient, such happens in the exact completion, but also we fill the gap because now we said that proof relevant elements for this doctrine, if C is weakly legs, are suitable cones, right? But we already met cones with exact completion. Pseudo-equivalence relations are cones, and they coincide in this case. And so we obtain that the extended elementary quotient completion generalizes the exact completion of a weakly legs category in its general form. And later we can define also what is an implication, existential, universal biased elementary doctrine. And we can generalize all those results giving you properties about the exact completion. For instance, those of Carboni, Rosolini, and later Menegger about the locally Cartesian closure of the exact completion of a weakly legs category. And here there are some references. Thank you.
So, if I've understood correctly, we still have strong finite limit structure on our fibers.
Sorry?
We still have strong finite limit structure on our fibers.
Strong finite limit structure on the fibers?
Yes.
Yes. Okay.
So, my question is, do you see a way of weakening that in your approach?
So you mean to weakness the properties of the fibers?
Yeah.
So for instance, so you just require finite needs and fiber equality. You mean to assume less than finite needs?
Or, well, this is happening in a closed set, right? So maybe we're happening this exists in free order, and then we have finite, we have weak finite needs in free order.
Okay. So, the fact is that if we have posits, I mean,
Exactly.
yeah, are necessarily strong, right? But if we do not consider posits, then this is a very interesting question because you can assume yes, weak properties if you have a category instead of a posit. Yeah.
One more question. Okay, so thank you again.